Good. So, okay, thanks again for the introduction. So my research group is working with structural health monitoring and NDT problems last almost 3 decades. So this is a long time from the last century up to now. And to go to the next, maybe here, yeah.
Yes, we need to click there. I neglected this. And now you can.
Okay, so that is the next. So the department participated in 22 international grants in this period as as coordinator. So you can see the list. That was the European project starting from FP6, FP7, Horizon 2020. We had the 2 grants from Boeing, from Airbus, from European Aerospace Defense System, from NATO, European Science Foundation, Engineering and Physical Science Research Council in UK, and Royal Society UK, and US Army. That was for 3 years grant also dedicated to my research group. So few information about those grants. So that is ongoing grants. The first is Bio-Inspired Hierarchical Metamaterials, which is led by Professor Nicola from University of Trento, and that is the group of university. You can see also that is ETH Zurich, but other group. Okay, hello. And the second group that is mentioned by Professor Eleni Hatzi, that is fusion of models or data for enriched evaluation of structural health monitoring. That is only bilateral project. Yeah, that was almost ongoing. We finished this grant. That was Turbo Reflex, Horizon 2020, Turbo Machinery, retrofits enabling flexible backup capacity for the transmission of the European energy system. So you can see many groups. And this project was led by Siemens Germany, but also there are groups, as you see, from many European countries. And the next project, that was CERT-Bond, that was Horizon 2020 project. That is CERT-Bond, that is a cost project, led by people from Holland, from TU Delft, relay the roadmap for certification of bonded primary structures. And that is 29 partners. And that is also interesting project, Horizon 2020, a quality assurance concept for adhesive bonding of aircraft composite structures by advanced NDT combo NDT. It was for 36 months, led by Fraunhofer, Bremen, and there are groups from Aeronova, from Greece, from ADS Airbus, from CAE, from France, Airbus Defense and Space from France, Astrium, etc. I will show you some results of this project later during my next presentation. And that is CNRS-PAN projects. That was a bilateral project between my research group and group of people from Poitiers and Paris. And that was eco-composites damage analysis using laser shock technology. So you can see some information. That was 3 partners from, as I said, from my research group from Paris and from Poitiers. Also very successful was project founded by NATO. We had 2 projects founded by NATO. That was on structural health monitoring of military vehicles. We had many lectures in Poland. There is the group of partners you can see from Canada, Germany, Greece, Portugal, Spain, etc. And we had many lectures in many places in Europe and also in Canada, outside Europe. Okay, that in the frame of FP7 Marie Curie action, we had the following project: new materials and reliability in offshore wind turbines technology. That was MareWind. I led this project. So we led the project, and you have many groups from Delft, from Leuven, from Liverpool, and that is from Norway, and some partners from industry. And in the frame of FP7 grant, we had ENCOM project, extended non-destructive testing for composite bonds. So we specialized last decade in composite bonds. The project was led by Bremen, Fraunhofer Bremen, but the industrial partner was Airbus from Germany, but also in collaboration with Toulouse, with Airbus France. And that was also a group from Switzerland. You can see EPFL from Lausanne, University of Patras, and CNRS and others. So the next, that was the previous COST project, novel and reliable optical fiber sensor system for future security of safety applications, with many partners listed here, 24 partners. It was ended in 2014, very successful. And FP7 Marie-Curie action, that was static and dynamic piezo-driven stream-wise vortex generator for active flow control. That was only 3 partners, but very good. LMS, no, 2 partners, LMS and our group. And innovative methods for separated flow control in aeronautics. That was more partners from Belgium, from UK, Liverpool, from Cedrat, from France, and from Poland. That was industrial partner in the last position. Okay, very briefly, that was project which I chaired. I led this project, Holistic Monitoring System for Wind Turbines. It was 2 years, from 2011 to 2012, and was dedicated to Baltic countries, means from Sweden, Finland, Germany, Poland, Latvia, some else. Okay. And we had 2 projects from Boeing, paid directly by Boeing company, that was dedicated to structural health monitoring, and we had common patent that will be later during my presentation. And FP6 project, structural health monitoring, led by European Science Foundation. And also some project in the frame of FP6, aircraft reliability through intelligent materials applications, led by Gamesa, now is Gamesa Siemens company. NATO project, that was the other, preventing disaster from collapse of aircraft structures using vibration-based health monitoring. And project paid by EADS, that is European Aerospace Defense System, structural optimization and resulting damage monitoring implications. That was from EDS military division from Munich. And also one project founded by the Royal Society, that was modeling of wave propagation and damage location structures, and EPSRC project with leading partner from Rolls-Royce, from Derby, from UK, University of Aberdeen, and University of Glasgow, of course, our research group. And one project dedicated only to my research group, that was a long time ago, in last century, but very important up to now, because we started with this topic, dynamics of cracked composite material structures. We started from this topic and we continue up to today. So that is 25 years experience in the composite materials and damage detection. Okay, some information about lectures. I participated in my research group in many lectures. That was in Udine, in the frame of mechanical school, also organized in Trento and in many other places. So that is, you know, I touch on this problem. That is also one photo from Vancouver University, when we had quite good in UBC, University of British Columbia, 10 days course on SHM application in military structures, and lecture project founded by European Commission in the frame of FP6, and we had lectures from 2007 to 2010 in many places in Europe, in Germany, Portugal, Spain, etc., etc. So you can see that I listed all of them. And some 2 words about our awards. You obtain, you know, Dragon Star award, that is European Commission award. You obtained the first place in 2015, as I remember correctly. So that is for innovation. The award was together with Rohan University and Hong Kong University and our research group. And there are people involved from my side in this, from Polish side. It's my name and, Pawel and other people from my research group. And also, that is my teaching activity abroad. So I had lectures at Syracuse University, University of Glasgow, University of Northampton in the UK, and École Nationale Supérieure des Arts, and I'm in Paris. That was as visiting professor in many periods, and reviewing doctoral theses in many countries. They are listed below. Between, not in Switzerland, but maybe in future, but in many places in Asia, in Australia, etc. And also quite recently, in 2019, I obtained personal SHM Lifetime Achievement Award sponsored by Boeing Company. That was an award which I obtained at Stanford University during the IWSHM conference. Some our books printed last decade, that is on guided waves in structures. This is by Wieslaw, New Trends in Vibration-Based Structural Health Monitoring and Structural Health Monitoring Encyclopedia. Wind, after the project, and adhesive, that is the recent book, Adhesive Bonding Aircraft Composite Structures. That was after our two research European projects. That is the copy of patent, EU patent with Boeing Company. From our side, 2 persons, Pawel and me, and from Boeing, there are some, the patent that was patented in 39 countries. That is my associate editor activity in some journals dedicated to NDT and SHM mostly. Okay, so where is my second presentation? Probably I skip this one. And this is quite big. Okay. Good. I would like to tell you a few words about a large problem which we investigated last decade, that is non-destructive assessment of structural integrity and failures for lightweight materials. And this topic we investigated with my research group. So the author of the talk would like to thank to co-workers of this research, my research team. Now that is my core research team, because my research team is much wider, but there are people graduated by me to PhD and to higher positions, such as Pawel and Rohan, you see, and other people. They prepared PhD thesis in period 2005 and 2016, as I remember correctly. I think that Rohan was the last from the. Okay, so that is online on my talk. That is an introduction, motivation of research objective, inspection of composite structures, and I will very briefly tell you a few words about NDT-SHM methods for surface assessment, for structural joints, and for method for damage detections. So we use, no, that is obvious that lightweight materials are very important in aviation and civil engineering, in mechanical engineering, in offshore engineering, etc., etc. There are some well-known information, how many carbon composites we use for Boeing 787, for Airbus 350, and for Airbus 380, and Eiffel Tower. You know, the rivets are compared to Eiffel Tower to Airbus 380, but of course different rivets and different problem. Okay, so now motivation is to enlarge our knowledge on the problem. So we use for this physicochemical physicochemical properties of the structures, defects, operational loads, and for investigation we use many Not all are listed here. Many techniques like control materials processes, structural design, extended entity, structural health monitoring, non-destructive testing, and that will be few words about that in few slides. Why this problem is very important? You know, I support my introduction using common work with a group from Patras. We published some papers on this. So you can see to the right, the stress intensity, GEI, that is strain energy release rate, which is completely different for healthy, means reference sample, and for others like poor curing, release agent, moisture, skydrol, thermal degradation, etc. So you can see that those parameters reduce the strain energy release rate. That strongly influence on stress intensity factor. So that is very crucial problem, and we undertake with many people to solve, of course, not all, but solve some problems. Here you can see possible sources of weak bonds. To the left, no, there are no all, but you can see that moisture, anti-adhesive agent, release agent, fuel, hydraulic fluid, de-icer, thermal degradation, improper adhesive curing, errors in bonding, fingerprints. So those parameters strongly influence in manufacturing process in some cases, and that is a large problem in services. All of them are, you know, are during the services. So taking this into consideration, we investigated the following problems. So the first, that is the study of surface of polymers reinforced carbon samples, degradation by, for example, moisture, thermal degradation, kiss bonding, etc., etc. The second problem, that is investigation of condition of CFRP bonds. So you can see that is the schemes, sample 1, sample 2, and degradation between the layers. And after bonding, we obtain the structure, and the next problem, that is degradation, mechanical degradation, like the lamination cracks, but not only, because also we include to this problem thermal degradation, for example, moisture or some combination, the icer, etc., etc. So research objective is evaluation of surface conditions before bonding, evaluation of bonded joint condition, and evaluation of damage detection, damage in wider meaning. So you can see here selected some methods used by people in adhesive bond quality. To the left, that is, there are methods, and to the right, that is advanced surface quality. So the methods, no, there are only samples, not all. So that's active thermography, terahertz, gigahertz reflectometry, nonlinear ultrasound, LASAT technique, laser ultrasound, active thermography, laser scanning vibrometry, electromechanical impedance, vibrothermography, ultrasonic, active thermography, and for surfaces, even more, because that is X-ray influence, fluorescence, reflectometry, infrared spectroscopy, laser scanning, optical simulated electron emission, active thermography, aerosol weighting, laser breakdown spectroscopy, terahertz again, optical fiber, electrochemical impedance, electromechanical impedance, etc., etc. So some of them I will very briefly show you today, and general overview on SHM and NDT methods is presented here. So you can see in one table, this is the most common NDT methods, like ultrasonic inspection, dye penetration, laser excited ultrasound, X-ray radioscopy, strain gauges, and other. Most common extended NDT methods, this is electromechanical impedance, active thermography using optical excitation, active thermography using ultrasound excitation, laser Doppler, vibrometer, terahertz, and some other. And most common SHM method, starting from the oldest vibration-based method, guided wave method, fiber optic method, techniques, acoustic emission, comparative vacuum monitoring, that is also old method, and electromagnetic layer, and others, that is not end of the list. So general problems which we should solve, which we consider, that is sensors, locations of sensors, implementation, measurements, modeling of structures, signal processing, visualization. So we, undertook this all problems in during this decade. And areas of interest: sensors, models, signal processing, temperature, damping, moisture, chemical contamination, nonlinear properties, and some others. So I will start with from modeling very briefly, because we investigated in 2010 before numerical methods using spectral finite elements. And we published even a book on this topic. That is the method similar to finite element method, but in our opinion is much better for some reasons, but that is no time to explain briefly even now. So we propose the following model for delaminated multi-layer beam. So the idea is to include the failure into elements, not like in regular finite elements. Usually failure is modeling between layers and between nodes, between layers, but the damage in our case is included to the element. And that is the 2D model for delaminations for plate. Again, we published this in 2007, you can see many years ago. That is some details. So if somebody, and also we publish 3D. We propose 3D finite elements with 216 nodes for the same method, means for spectral finite elements method. The other method which we investigated in my research group, that was electromechanical impedance, and that is the ongoing problem: laser fluorescence, laser vibrometry, and active thermography, and terahertz spectroscopy, which is very effective for some cases. There's equipment in my lab. So you can see that is the terahertz laboratory in the institute. No, there are some details, so if somebody is interested, we can discuss this later. And now we start with some results, few methods: inspection of composite structures, and they are presented in DTSHL method for surface assessment. As a first, you can see the vibrothermography, the influence of temperature and humidity. So no, there are some details because we have the climate chambers. We can cool the samples and heat the samples from minus 70, I think, to plus 300. No, there are some details. I don't want to explain this, but we use this technique very effectively to investigate this problem. So influence of temperature and humidity on the health of the structure. Okay, the next, there are some information about terahertz spectrometry, detection of location of faults. So you can see to the left, that is the sample with delamination, and to the right, you know, B-scan and C-scan for some effects. And we also included to this analysis optical fiber between the layers, and we observed delaminations as cracks. So there are everything details are presented to the right. That is electromechanical method, for moisture detection. So you can see the equipment, the sample, and the sample was immersed by water. And with in very small percent, because the mass was 36 grams. It was 2.7% of the total mass. And we immerse the sample with water, and later we observe the effect of drying after 1 day, 2 days, etc., etc. And you can see the plots. To the left is some details, how change frequency and versus the resistance for in ohms. So that is quite effective working method. Here you can see the same technique used for release agent and for moisture. To the left, release agent in very small percent, because that was only 2.5 up to 10% in atomic scale. That is very small, really, and that was silicon. And you can observe how this parameter, G, dropped down from over 1,000 to 40. And we use for this RMSD technique. And to the right, you can see how the moisture, water in very small percent, the maximum percent, as you see, this is 1.25%, how influence on GIC parameter and to stress intensity factor. This method works. There are sample of terahertz application. So you can see, we observe the Teflon insert impact in GFRP, the lamination and moisture on the surface of the sample. And in the next picture, you can see some details. That is transmission measurement. That was surface water contamination. And in the bottom, the amplitude drops twice due to the water. That is interesting task. That was terahertz spectroscopy and thermal degradation. That was collaboration with, I think, Airbus company, because we observed the states. You can see the states from 1 to 8 with different temperature and with different time of heating. So you can see that the samples were heated from 1 hour to 6 days, but in each state the same hours. And we use for this Mahalanobis distance method. So as a sample, you can see 3 states, state 8, 3, and 0, and Mahalanobis distance between the reference state and the further step of heating. So as you see, this method works quite good. Now that is repeated, some for different samples and for different stage. That is damage detection using terahertz technique. So the scan area, thermal degradation, and you can observe the view of composite layers and the bondings. Maybe I skip this one because that is similar to the previous. That is damage detection using terahertz techniques with the different, thermal degradation. You can see some samples in this place with quite long heated. Yeah? So we observe that the optical delay using this technique. And in the next picture, you can see laser in fluorescence, which we also use in my research group. And we heated samples up to 450 centigrade and kept the sample 5 seconds, 10 seconds, and 30 seconds. So you can see that is visualization, and you can see distribution of fluorescence intensity at different times. Good. I think that is similar, and you can see in the diagram the heating time for starting from 5 seconds up to 30 seconds. And of course, we have some visualization process and use integral of area below the intensity curve. I think that is similar to, I skip this one, and that is the laser fluorescence method detection of chemical contamination in composite specimens. You can see different temperatures, and we try to show the influence as a diagram to the left. That is the density of fluorescence, and that is in the horizontal axis, there is the reference state and some temperatures. There are real temperatures used for this type of composites. So you can see how temperature change from 190 to 2010 and what happens with the sample. Okay, that is thermography and detection of water drop. So this is similar to former presentation, and that is active thermography, which we use for damage detection. We use ultrasonic excitation, showed here, and also use halogen lamp for that for excitation, and you can see results for both techniques. In upper row, that is for ultrasonic excitation, and for halogen lamp is in the bottom. And the next is inspection of composite structures, methods for structural joints. So well, that is the same idea which I presented before. We have two samples and we join, and that is adhesive. And of course, we have some imperfect, we assume that there are some imperfect adhesive bonds. So for example, SFRs, that is poorly cured adhesive. as this, and there are some information detecting damage in composite using elastic wave propagation. And in this case, we use electromechanical impedance, and very interesting, we propose interesting techniques, that is Frishet distance, that is established on, on the admittance and conductance and suspectance. But I show you results. For example, for adhesive bonds affected by release agent contamination and moisture contamination and poor curing, we observe different plots. Sorry, that is very sensitive. So to the left, you can see the green dashed line, that is bonded symmetric sample cured at 180 degrees. And there are blue line, that is for release agent contamination, for the curve is for moisture, and PC is for poor curing. So you can see differences, and that is very important because we would like observe differences in each sample, what happens. So we can use different, techniques for evaluation this process. That is, I think, similar, but that is comparison between curves using the so-called Frishet distance for different contamination. So to the left, you have contamination by water from 0.45%, very low, that is the red line, up to the black line, that is 1.25, still very small contamination. And that is contamination by water, and that is curing with, to the right, you can see three curves. The first, the red is reference, and the blue is for temperature 160, and the black is for 160 and 150. But still, we observe some differences, and that is the conclusion for this method. That is laser Doppler vibrometry for pre-bond contamination with moisture. So you can see some points for different states to the left and to the right for poor cure of adhesive. So this method is effective because comparing with reference state, which is here in this point, and other points, you can see that this method is really very sensitive. Terahertz spectroscopic detection of delamination. So we use for this C-scan and B-scan and C-scan. That is the sample and equipment in the top row. And there are some details for A scan and measurement points, delamination, the metal tape, etc., etc. You can see some diagrams. And for B scan, similar case. So that is the referential state to the right, and B scan delamination. So delamination is visible in this place. That is the C scan. And for C scan, we observe, again, delamination in this area. This is magnification of this point, which is visible here. Okay, and now a few results for biocomposites. That is we use for the Terahertz spectroscopy. That was our work with CNRS in Poitiers. And that has maybe that was, I think, maybe this point is that is ultrasonic test for contaminant that was published. This evaluation of adhesively bonded composite by non-destructive techniques that was presented 5 years ago. Also very interesting research, but ultrasonic technique is classical, so maybe that is not so interesting today. Inspection of composite structures for structures, joint structures, and I very briefly tell you about some results from last decade. That is guided wave scanning laser vibrometry. That's our equipment which we use for many details. You can see that is, for example, stabilizer from a real helicopter. So we had collaboration with one company, and there are some results. I think that most of you are very familiar with this technique, so you can see some details. For example, in this point and this point, we observe some imperfections, means that is some failure. There are the mode conversion, very important problem, especially in composite materials. So we tested this problem, and also you observe some details how we looked for this, we notice this behavior. Okay, that is numerical modeling of using spectral finite elements methods. So you can see two blades, which we modeled and observed the wave propagation. And in the bottom, that is the model of plane wing. Also is failure, for example, located in this place, and observe changing of wave propagation. There are guided wave scanning laser vibrometry used for different applications. So you can see we found here, observed stiffener and bolted joints and rivets, etc., etc. So there are many, and what was important, we observed the conversions of modes in such cases. That is damage localization elements, manufacture of composite structures with different failures. For example, here you can see the glass reinforced composite panel, filled cell aluminum and elimination. Here was the bonding of stiffeners and some maps, RMS energy maps in the bottom. And that is the damage localization element manufactured in composite structures. That is the model of this stabilizer, real helicopter stabilizer with many failures distributed in the plane, and visualization, that is energy distribution. And we continue out, that is the presentation with different excitation, means from 16 kilohertz to 100 kilohertz. Sometimes using higher frequency is not so good because it's strong damping in composite materials, so wave propagates not so far, and also is very effectively damped. Okay, and now that is also damage localization, composite aircraft structures. We have here real aircraft structures and some tests using guided waves and visualization. Now, conclusions are, I think, obvious that the presentation of method of testing lightweight materials, I tried very briefly discussed methods which we use. The method used in testing mechanical damage are presented, several methods used in examination of mechanical methods, several methods of physical and mathematical modeling, and the effectiveness of using several signal processing methods was indicated. And also possibility of practical use of developed method was suggested. That is not all, I can tell about this much longer, and but no, I received only 20 minutes. I think that I passed this time. Okay, sorry. Thank you.
Thank you very much. I suggest, should we take questions now, or would you like to complete the round? So let me pause the recording for now.
Okay.
It would be better to have questions now than any.
Yeah, so let me pause the recording.
So now, okay. So maybe I will try to.
Okay. So I am Paweł Kudela. I'm associate professor at the Institute of Fluid Flow Machinery, and I would like to present you the topic about spider-inspired phononic sensor for damage detection and localization. And this is this research is in collaboration with Professor Nicola Pugno and Marco Miniaci, and the other names are from our team. And this is oh, it's not. Okay.
You have to click first on the left.
Okay. Yeah. Okay. So this is just a part of a larger project, BOHIM, which is entitled Bio-Inspired Hierarchical Metamaterials. And the aim of this project is to develop a new class of mechanical metamaterials for wave and vibration control. And this research is conducted at varying scales from ultrasound through acoustic waves and ocean waves for vibration harvesting and seismic waves. And Bohim gathers researchers from like University of Trento, CNRS, EMPA, ETH Zurich, also Imperial College of London, University and Politecnico di Trento, our institute, and two small medium enterprises, Multiwave and Phononic Vibes. I don't know if everyone is familiar with the metamaterials. Yes. Yeah. Okay. So I don't have to like introduce definition, etc. Okay. So let's me go further. So our aim is early damage detection and localization in structures, and we have some idea how to implement it by using three components, which is contact acoustic nonlinearity, guided wave filtering by using this type of phononic crystal, and the time reversal method actually for damage localization. So I will present you a little bit of initial research work, and which led to the design of this spider-inspired phononic crystal sensor, and I will show you some numerical and experimental results. So this topic of early stage damage detection is very important, because even a small hidden crack or fatigue crack introduced through manufacturing on initiated during flight, for example, can lead to catastrophic failures. We want to utilize nonlinear effects in signals of propagating waves for this early stage damage detections, and then this design this sensor for filtering part of the signal, and then use the time reversal method for damage localization. And I will show you details about each step. So in 1966, there were first papers related to sideband harmonics and higher harmonics utilized by forced nonlinear vibrations, and this were further extended, and it was shown that this is caused by clapping and Arabic mechanics, for example, at delamination composite materials. And this also can be further utilized for imaging of defects by using a nonlinear wave modulation spectroscopy or elastic wave spectroscopy. If we have signal of the wave packet type, and we will apply it to a linear material, the output will be of similar shape, and the spectrum of frequency of inputting signal will be similar to the outputting one. But if we apply the same signal to nonlinear material, the signal which we register will be deformed, and we will look at the frequency spectrum. Apart from the main harmonic around the F0 frequency, there will be higher harmonics and subharmonics. So we want to utilize this effect. And there are plenty of examples in the literature which this effect is utilized. For example, on the very left picture, you have higher harmonics due to this bond. On the second examples, there is like higher harmonics due to delamination. And even such a thing like a corrosion can introduce nonlinearity, but this is not like contact acoustic effect. It's a different one. It's nonlinearity in the material. But like as you can see, the second harmonic is barely above the noise level. For contact effects, these effects are a little bit higher, but still the amplitudes of higher harmonics are like 10 times or even more lower than the main excited harmonic. Our idea is actually to filter out the main wave harmonic, which we are exciting, leaving only all effects caused by nonlinearity. So the idea is that we are exciting waves at point A, then the wave propagates, and when the wave encounters defects, this will rise the nonlinearity like F2 and F3 on this graph, and which will further propagate through the ultrasonic device with periodic arrangement of cavities, which will filter out this F1 harmonic. So we will have only nonlinear effects, and then we can threshold the signals so that we know that there is like a damaged or undamaged state of the structure. So far I talk only about damage detection, but this can be further extended for damage localization. And for this case, we want to use the time reversal method. I am co-author of the paper, which was published in 2019, which uses this method for impact localization. But actually, the same concept can be used for detecting of nonlinearities, which will come out from cracks, for example, or delaminations. So idea of the time reversal method is that we excite the waves at point A. This waves comes through the structure and it's registered at point B. Then it is time reversed, and this reverse signal is again applied at point B. And due to reciprocity conditions, the waves will refocus again at point A. So if our point A is like a point of generating nonlinearity, so we will have like refocusing effect of this waves at this particular point. So that's the idea. This will be probably better visible later on when I will show you some numerical simulations. So the idea of this phononic crystals comes from 2017. So this was like a first proof of the concept. There was a plate with attached two phononic crystal type parts, the linear one, PC1, and the like C-shaped PC2 were attached directly to the edge of the plate. So the thing is that this type of sensors has to be of the same thickness and the same material as the host structure. So this is like limiting us. The PC1 type of sensor has to filter out waves, whereas the PC2 was designed to like focus waves at point B on this graph. And PC1 has a band gap around 172 to 244 kilohertz. So this was the part for filtering this frequency range. So in the POHIM project, we would like to reduce this limitation and design this sensor differently so that we can place it on the top of the surface of the plate so that we can monitor structure of various properties, not only metallic, but also composite. Yeah. So we took inspiration from spiders. These are one of the most vibration sensitive creatures, topped out only by cockroaches actually. And they have a clever sensory system embedded into joints of their legs. And this is called a slit organ because it looks like several slits in the joints of the legs of different angles and dilatations so that they sense waves in or vibration in different frequency ranges and wavelengths. However, this is for low frequencies, like below 1 kilohertz. We actually are interested in higher frequencies, but we took inspiration of this vibration sensing concept to place sensors near the legs of the spider. Like a spider has, like almost all spiders have 8 legs, and the body is divided by cephalothorax and abdomen. So we want to place sensor when each leg joins the cephalothorax part. And actually there is a quite interesting paper in Nature when scientists try to mimic this sensor by nanoscale crack type sensor. But we are not doing it. We just using the global idea of sensing, and want to utilize this vibration sensitivity action. Maybe I'll add that courtship in spiders is very tricky, and the male spider has to introduce themselves by plucking the strands of the spider with a certain frequency. Otherwise, it can be eaten because it can be mistaken by prey. And the female spider is actually bigger, so it's easy to eat the male spider. So we took this inspiration and we started by the designing of the spider like a sensor. And we started with like 6 unit cells, but numerical simulation shows that only 4 cells are enough for this blocking of unwanted waves. So the size was smaller, so it's easier actually to simulate these effects, but still it's very huge task, like 4.8 million degrees of freedom. So in COMSOL multiphysics, it takes to simulate one case like in 3 days. So our first concern was the fact that the incoming waves to the spider can be reflected, and maybe there is lost on efficiency of incoming wave to the spider. So we make some simulations, and the idea was to have as much energy and amplitude on the spider on the top here, coming from the excited waves in the plate. Actually, this presents 2 things at once. The deformation shows A0 mode, but the color scale is showing S0 mode, which is more in-plane behavior. And the next slide shows like parametric studies when we change the angle of the spider feet. So when the angle is like 90 degrees, there is a lot of reflection, and actually the amplitude on the top is small in comparison to what is propagating on the bottom part here on the plate. But when the angle is small, the amplitude on the top is comparative as the amplitude on the bottom. So if we combine this in the one graph, you can see that we are mostly interested in the range between like maybe 1270 degrees, because there is still high amplitude at the sensor location, and the leg is not excessively long. We don't want to have like a spider with very long feet. So the next was experiment to confirm the band gap. So the spider was actually made from a flat sheet of aluminum, 3 millimeter thick, and the unit cells were cut by laser And we scanned by laser vibrometer the spider. So at point A, we put a piezo transducer, which was exciting a chirp signal. And the sensor measured the signals at point S1 and S2. And these are the results. Of course, the S1 is on this very close to actuator, and the whole wave goes to the S1. But when the waves comes through the leg, you can see a significant drop of magnitude. So it confirms that actually the band gap is around 200 kilohertz. So it confirms that we wanted the band gap in this area, and it is there, essentially. So maybe I will pass this spider. Is already crippled because there is one problem, is a design flaw, I would say. So that wall thickness is very thin behind this unit cell and the edge of the leg. So it is breaking easily. So now we are working on the updated version. So we optimize this unit cell to have the same band gap width, but to have like a thicker edge between the unit cell and the leg, so that it will not break. And maybe we'll just print it, 3D printed it instead of laser cutting, because this is not the best method for doing it, but it was made for free, so I cannot complain about it. Okay, so this is exemplary simulation. So we're exciting 200 kilohertz here, and then there is like 400 kilohertz higher harmonics due to nonlinearity. And this nonlinear harmonics coming to the inside of the spider, whereas these 200 excited are just reflected from legs. So there is a lot of going on. There are reflections from edges and spider legs. And this is the first step. Let's go further. Next, we reverse signals and excite in this 8 transducer, let's say. And if you watch carefully, at a certain moment of time, we'll have a refocusing at the image location. Sorry. I don't know why it stopped for some reason. Okay, never mind. So this is like extracted one particular time, and you can see that at point D, where is our damage, there is a very high amplitude, showing perfectly that there is a location of damage. And we can even remove the spider to have like imaging on the plate. As you can see, there is a high signal to noise ratio, and it shows very clearly where the damage is. So this proves, at least numerically, that this is working. So that's it from my side. Thank you for your attention, and I'm open for questions.
Sorry, let's.
Hello, everybody. I'm going to present some interesting work that I've been doing, sensing guided waves using optical fiber grating sensors. FBGs have been around for the last 2-3 decades, and they have been, I would say, they are even very mature technology for strain monitoring in general. But the sensitivity for ultrasonic guided waves measurement was quite low, but through some developments in general, especially in the optical field, Now it is possible to use them for guided wave sensing, and we are looking to harness them and some very specific properties that the optical fibers provide. We are going to maximize their effect for damage detection and localization. Okay, actually guided waves, I guess Pawel gave a very good overview of it. So I can skip this, but basically they are lamp waves, which are superposition of longitudinal and shear waves. They can be used for low levels of damage detection, non-contact measurements through laser Doppler vibrometer. But unfortunately, it becomes challenging to monitor composites because of their high attenuation, and then you would need a lot more sensors. So if you put a lot of piezo actuators and sensors on it, the added mass of the wires is a complicated challenge too, and it is very labor intensive as well. So we are looking at better options. So FBG sensors appear as a good solution to this because you can multiplex FBG sensors. So on just one optical fiber, which barely weighs anything, you can have multiple sensors and use them to detect. Traditionally, it was used in the wavelength division multiplexing form. So over here, you can see in this first figure. Can you see the mouse? Laser. No, it's okay. I can show you. Over here, you have a FBG sensor, and this is how you can put a broadband spectrum in it. The FBG acts as a selective filter of it, and you can measure the delta lambda and determine the strain or temperature in the FBG sensor. But the delta lambda, or the change in the wavelength when ultrasonic wave is propagating, is very low, and you don't get a very good sensitivity. So in order to counter that, something known as the amplitude-based edge filtering approach is used. So over here, when the strain changes, the peak of the wavelength shifts towards the left and the right. But if we are, instead of determining the delta lambda, or the change in the wavelength, if we use a pre-amplified photodetector, you can look at the change in the optical power that is emitted. And because the slope of the FBG spectrum is quite high, even a small strain change over here will give us an amplification and a higher sensitivity. So this can be leveraged to increase several fold the sensitivity of our sensors. On top of that, in the traditional way, when FBGs are used for strain localization or strain measurement, the FBG is bonded onto the structure. And the adhesive, which is used for putting the FBG, kind of restricts the movement of the FBG and affects its sensitivity. So it can be used in a remote configuration, as shown over here, for improving the sensitivity. So the optical fiber is bonded to the structure, but not at the location of the FBG. The guided wave, which is propagating in the structure, gets coupled into the optical fiber. So the symmetric S and the A waves, which are propagating in the structure, get converted into the longitudinal and flexural waves into the optical fiber. The optical fiber is not only an excellent waveguide for the optical light, but it is also a very good waveguide for the longitudinal and the flexural mechanical waves propagating in the optical fiber. And they can propagate several meters with minimal damping and attenuation. Also, the waves propagating in the optical fiber in the sub-megahertz range are non-dispersive. So that makes signal processing much easier. And because the FBG sensor is not constrained because of the adhesive anymore, you get a higher response, almost 81% more. So which is also quite good and required. But the sensitivity, even though high, it shows quite a few peculiar characteristics because the FBG sensor is extremely directional in nature. So for the directly bonded FBG, it shows a cosine squared relationship. So based on the angle of propagation of the wave and the relative angle to the optical fiber in which it is bonded, if it is in the direction of the optical fiber, you have a very good sensitivity. And as the angle increases to perpendicular, you get at almost no value in the sensing. This is quite expected, and there have been some efforts to overcome this. But we can actually also use this as a benefit, this relative sensitivity. Also, another peculiar characteristic is shown is if it is directly bonded. When the FBG is bonded to the structure, it shows a cosine squared relationship. While it is in the remote configuration, it shows a cosine relationship. So this difference is also can be used to enhance the knowledge of the waves propagating into the structure and can be maximized for damage detection. Also, the FBG sensors, unlike the piezo sensors, which can be used as sensors as well as actuators, FBG sensors are passive. So for the same structures, if you have, let's say, 6 PZT actuators and sensors, so you have 6 choose 2 paths for the wave propagation. But on the other end, in a FBG, if you have 5 piezos and 1 sensor, you have just 5 choose 1. So this passive nature has to be overcome as well. So this is what we did. In order to overcome the passive nature, we used the edge reflection approach, where if a wave is propagating along the structure and it meets the edge of the structure, it gets reflected. So this reflected point can be used as a pseudo sensor to enhance the number of actuator sensor paths that we have, and that can be later on maximized for damage localization. In order to image the damage, we use the ordinary elliptical approach with exponential weighing. So you estimate the time of arrival of a point on the structure where the damage is, and if it matches correctly with the experimental, you will get a very high agreement and a very high value. But if it doesn't agree well, you will get a low scaling of it. So this can be used for damage mapping and localization. So this was the output. In order to achieve the edge filtering approach, instead of using a broadband spectrum laser that is used for ordinary FBG measurements, you use a tunable laser which is tuned onto the upward slope or the downward slope of the FBG, and then an optical circulator to channel the light coming from the port 1 into the FBG. The reflections from the FBG are channeled into the port 3, where a preamplified photodetector can be used for sensing. And this was used. In this application, we had only 2 actuators placed onto the structure, marked with the crosses over here, and the sensor was at the middle. So in theory, we had only 2 actuator sensor pairs. So for damage localization using triangulation, this is not a sufficient condition. So you wouldn't be able to localize damage uniquely. So you can see over here, based on the time of arrival estimation, you get ellipses for the different peaks that are seen in the time signal. And those, the 2 of the brightest ellipses intersect at locations D1 and D1 dash. So there is no way as of now for us to determine if D1 is the actual damage or the D1 dash is the actual damage. So that's where we use the edge reflections and enhance the number of actuator sensor paths that are in way. We determine the paths that are passing through the locations D1 and D1 dash and take the ratio of the relative RMS in the healthy and damaged case. And if the ratio exceeds a certain threshold, you say that the damage is detected. Over here, the red shows the paths that are passing through the damage, and pink are actually the locations which are not, but they have the same time of arrival of the reflections. So that's why a 2-step approach is needed. In the first, we identify a possible location or a hotspot, and out of those hotspots, you use them to localize the damage in the second step more accurately. In order to localize damage with this mapping approach, you have to determine the pixel value of the entire structure. So it is computationally more demanding. So we were looking at more options to reduce the computational load. So we utilized a piezo-based damage localization for the same set of data. And we were able to localize the damage with 1/3 of the number of computations. And it was able to converge onto the exact solution on every run. As long as the number of starting particles was high enough to ensure a good global search, we were able to localize damage. So this is also something that we have been working on recently. As of now, this is like just basic damage detection and localization, just replacing the ordinary actuators or PZT actuators and sensors with an FBG sensor. But where the FBG sensors really come into their own are the unique properties that they show. So for instance, they can be used for mode filtering in the measurement. So as I mentioned before, when the FBG sensor experiences a uniform strain, you will get a shift of the FBG spectrum towards the left or towards the right based on the contraction and expansion of the FBG. But if the FBG is exposed to a non-uniform strain, instead of shifting of the FBG spectrum, you will see it elongating or contracting. And if you are able to determine the shape of the FBG spectrum, you might be able to use it for mode filtering. So we tried this method on a simple aluminum plate. So over here in this table, you see the relative of the wavelengths of the A0 and the S0 wavelength for a 1 millimeter thick aluminum plate at different frequencies. And in the brackets, you see the relative ratios of the wavelength of the guided wave to the length of the FBG. We were using a 1 centimeter long FBG. So at 250 kilohertz, what you see is there is a small video that shows the S0 wave going and then the A0 wave, and you can clearly see the difference in the wavelength of the A0 and the S0 in this condition. So this difference in the wavelength can be used, can be sensed by the FBG sensor because of the relative difference in the wavelengths. So for instance, at the 50 kilohertz, the ratio for A0 is 1.35 and for S0 is 10.17. So they are both in the same regime where you can expect a uniform strain over the entire FBG. But at 250 kilohertz, the regime is different for the A0 wave. So a ratio of 0.56 shows that there will be non-uniform strain caused by the A0 wave, while the uniform strain caused by the S0. So if we are able to sense this, you will see. So we measured we swept the wavelength of the entire FBG spectrum and measured it over a period of 8 minutes. But because of the whole synchronization process, they were very repeatable. And we were able to determine the mechanism in which the wave was coupled into the optical fiber. So for a 250 kilohertz, if you look at the elongation and the compression of the FBG spectrum, you can see that the A wave is amplified while the S wave is barely seen over here. Over here, this is the measured signal or the input using a piezo. While if you are looking at the delta F WHM, the S wave is barely seen while the A wave is amplified. On the other hand, with the delta lambda or the shift in the spectrum, the S wave is properly seen and the A wave is barely seen. So this phenomenon can be used for mode filtering. This phenomenon is not seen at 50 kilohertz because they are in the same regime of the relative ratios. So this is the proof that you could, like in this damage localization, we were using A0 wave for the damage imaging. So if you are able to remove the effect of the S0, you have fewer ellipses. So there is a less confusion about which is the actual location of the damage. And you get a better damage map and hence a better damage localization. Another interesting phenomenon that can be used for mode filtering with optical fibers is the birefringence of the FBG. So if FBG is introduced to a transverse load, the FBG spectrum that you see is split into two. To the long side of basically the cross section of the optical fiber, which is circular, becomes more elliptical, and then you have the long axis and the short axis, and the reflection pattern changes from a single peak over here to two peaks. And because of the relative directions of the guided waves which are coupled, each of these lobes have a different sensitivity to the S and A wave. So this can be used for mode separation as well, in theory, but there are several challenges associated to it. We introduced this birefringence by putting a load cell and transverse loading on the FBG, and we measured the response at 4 of the points, so on the upward and downward slope of each of these two peaks with different loads. In order to enhance the S0 and A0, we use two actuators on either side of the plate in phase and out of phase. What you would see is one of the peaks is more sensitive to the S0. So the upward slope and the downward slope of one of the peaks is more sensitive to S0, giving a marginally but around 12% or 15% increase in the amplitudes as compared to the other mode, while the other lobe is more sensitive to the A0, giving a 20% more increase in the amplitude. Unfortunately, this technique cannot be used on real structures because of the artificial loading that we have imposed. We are changing the boundary conditions. So the fundamental waves that are propagating are not the same as they were before. So this is something that was just a proof of concept. The real application of this can be done with embedded FBGs in composites, where if the FBG is embedded in layers which are perpendicular to the FBG, you see the splitting of the spectrum naturally, and this can be used for detecting the different modes separately. So some of our work was also done with the optimization of the actuator and sensor system. As I said, that the sensors are passive in nature, so they have to pair with actuators in order to have a actuator sensor system. And also because of the directional sensitivity, there are several challenges associated with attaining a good coverage of the damage detection and localization. We used it to determine the cost function, which came from the technique that I had shown before, where we were using the intersection of two ellipses, so coverage with at least two actuator sensor pairs, and then coverage from the edge reflections. We optimized the locations, and based on our analytical implementation, we chose some damaged location points in order to validate our results, and our analytical model was in excellent agreement with what we saw in experiments. We also study quite a bit of this because the physics of the whole wave coupling is still being understood properly. So having a numerical model which mimics the physics of the system is very important. We were able to develop a model that mimics the wave propagation in the optical fiber quite efficiently. If you use Abacus for the same simulation, it was taking of the order of 40 minutes on a normal office computer. I don't remember the specifications, but for the same computer but with parallelized code, we were able to achieve it in 6 minutes using the in-house development code. This is important because typically you are working with really large spatial scales and temporal scales. Typically your sample is 1 meter or some order of a meter in dimension, but your optical fiber is 125 micrometer thick. So you need to have really small mesh size for a large spatial scale. On the other hand, for temporal scale, you're typically looking at 1000 microseconds of simulations, but your time step has to be of the order of 1 into 10⁻⁹ or 10⁻⁻10. So that means the number of steps that you will need is also quite high. So having an efficient model which mimics the physics is also important. One very interesting new study that we have been doing is in the acoustic coupling. As I had mentioned before, that the wave propagating in the structure gets converted into optical fiber wave and propagates along the optical fiber. So if we are in olden days, if we can fuse two optical fibers, this wave can continue propagating in the fused optical fiber, and you can sense it at a later location. But using fusion on site or in real application is not easy because it needs very pristine conditions. So instead of having a fusion coupler, we just used an acoustic coupler using ordinary cyanoacrylate glue. Just a drop of cyanoacrylate glue spread over 1/8 of an inch can transfer around 20% or 22% of the acoustic energy from one fiber to the other fiber. And practically you can have multiple such fibers. So over here we achieved a 3x1 coupler. So basically 3 bonds without any sensor on it were made onto the structure, and one of them had one FBG located further along the line. And by having different lengths of these connections from the bond to the coupler and to the FBG, we were able to time separate the responses from the three locations which are bonded. And once you have this, you can basically use it as a data from 3 different sensors and use it for damage localization as you would. And this is very efficient because you can practically reduce the cost of equipment by 66%. Higher coupling is unfortunately at this moment quite difficult because you lose the signal to noise ratio significantly for a bigger couplers. But we indeed use this for damage localization with one FBG, and we were able to localize damage without any problems. So that's all from this. In general, like, it is a very attractive field, and some of the opportunities that the FBG sensors offer are unique to them. Also, I didn't cover some new other techniques that can be mixed with them, like self-referencing, where you can have reference-free damage detection with using only one sensor bonded at 2 locations. Also, polarization maintaining FBGs are inherently more sensitive to one wave than the other. So the same concept as the birefringent can be achieved through the polarization maintaining FBG. And this is what we are looking at, to employ the FBG sensors for reference-free damage detection. Thank you.
Thank you. Okay.